So section 5.4 is going to continue working with integrals, except this time a lot of our integrals are going to look a little bit different. So in particular, you've got stuff like this one right here, which says find the general antiderivative of the integral, or find the general indefinite integral. Now, when I write these things without upper and lower limits, that is, it's no longer a definite integral, it's an indefinite integral. That's where this thing gets its name from. Basically, what this is asking you to do is find the antiderivative of what's ever in the function, what's ever in the integrand right here. So here and here, here and here. That's what you're being asked to do when there's no limits. And that's fine. It's just reversing the operation of differentiation. It's finding the antiderivative. In fact, when we're working in section 5.1, I had a tough time personally not just writing down this integral symbol. Wanted to wait to section 5.4 to get there. Before we do one of those problems, let's take a look at this one. It says state whether the following is true or false by differentiation. So what they're asking you to decide is this true? Well, if this is true, then this function to the right here that I'm going to circle in blue should be the antiderivative of the integrand. Is it? How could I check that what I have circled in blue is the antiderivative of what I have circled in yellow? How could I check it? By differentiation. What would I differentiate and what would I have to get?
The antiderivative.
Differentiate the antiderivative, and I should.
You want to get the derivative.
Yeah, I want to get the integrand. Is the fancy word there? No problem. No problem. So let's take a look here. I did that work for you. If you differentiate, let's see, did I do this backwards? Yeah, I don't want to find the derivative of that. I want to find the entered. So if we differentiate what's in blue, we should see if we get what is in circled in yellow, the the function here, the integrand. So let me get rid of this, because that's wrong. We need to differentiate this and see if we get what's in the integrand. So let's go. And this is just some good work and practice with finding differentiation. And I'm going to start out with -3 times the square root of 1 plus x squared over x plus a constant. And we'll differentiate that. We'll see what we get. It's going to be d by dx. Now, the nice thing for us here is that the derivative of a constant is 0. So we can just focus our efforts on differentiating this. This one, I don't think there's any real nice way to get around using the quotient rule. You're kind of stuck with it. I am going to rewrite this as something to the 1/2 power. So we'll do d by dx have -3, 1 plus x squared to the 1/2 over x. So for the quotient rule, you're going to square the denominator, and it's going to be the denominator times the derivative of the numerator, which is going to be -3. And then that's going to come out front, 1/2, times derivative of the inside, so 1 plus x squared to the -1/2 times derivative of the inside, which is 2x. So that's the denominator times the derivative of the numerator. And then they need the numerator times the derivative of the denominator. So minus the numerator, which is -3, 1 plus x squared to the 1/2 times derivative of the denominator. the denominator is just 1. Boy. Now we got a lot of cleanup to do. The 1/2 and the 2 should cancel each other out, so I can take care of that. And I got an x minus 3 and another x, so I get a total of a minus 3x squared, 1 plus x squared to the negative 1/2. Minus and a minus is a plus 3 times 1 plus x squared to the 1/2 all over x squared. Now, a while ago, I showed you a little trick when you're factoring stuff like this, and that was to factor out the largest negative exponent. So let's factor out a 1 plus x squared to the negative 1/2. I'll also factor out a 3 here. And do I want to factor out the negative 3? Sure, why not? So I'll factor out a negative 3. That's going to leave behind an x squared. And then this will change sign because I factored out the negative. I'm factoring out that, so it's going to leave behind 1 plus x squared to the first power, all over x squared. Now, a lot of nice things happen here all at once. This x squared and this x squared cancel each other out. This comes down to the denominator, and I'm left with negative 3 over x squared times 1 plus x squared to the 1/2. Whew. All right. How does that compare to our integrand? I think I'm off by a negative someplace. Oh, I know where it is. Yeah, right here. That's going to be so right here, I'm left with a negative 1. Negative 3 times negative 1 gives me a positive 3. So overall, 3 over x squared. This is the square root of 1 plus x squared, or 1 plus x squared to the 1/2, same thing. So it checks. Whew. Phew.
How did you get the 1 plus x squared to the 1 again?
When I factor this out, you end up dividing each term by 1 plus x squared to the minus 1/2. So it'll cancel here. And when you divide this by that, so you have 1 plus x squared to the 1/2 divided by 1 plus x squared to the minus 1/2. These have the same base, so you subtract their exponents. 1 plus x squared to the 1/2 minus negative 1/2 becomes a 1, or the first power. So that's why that became just to the first power right there.
Oh, okay. Thank you.
Yeah, it's not easy to see. Don't worry, I'll put no more than a dozen of these on the exam. Actually, if I did put one on the exam, I would choose it to be a lot more user-friendly, because it's not really what I wanted from this example. I kind of expected the differentiation to be a little bit more straightforward. But let's go back to, Aspen says hi. Let's go back to the basic idea here, and that is that when you're trying to work with an indefinite integral, you need to find an antiderivative. So let's work with this one and actually get busy working with our antiderivatives. So integral of 2 plus the square root of x plus x over x. Now I saw somebody do this on Monday, and that is somebody integrated the numerator and integrated the denominator. You can't do that. There's no quotient rule. You can't distribute the integrand to both the numerator and denominator. But what you can do is what we did earlier, and that is divide all these terms by x. So square root of x over x plus x over x dx. Now you're going to get some simplification here. I'm going to leave this as 2 over x, but this is going to simplify, keeping in mind that that's really x to the 1/2. That's going to simplify to 1/2 minus 1 or negative 1/2. And now it's a matter of finding antiderivatives for all of these things. So let's take a look at the first one. The first one I can treat as 2 times 1 over x. Can anyone tell me what I differentiate to get 1 over x?
ln.
ln, nice. So what I get out of this is 2 times ln plus, add 1 to the exponent, gives me x to the 1/2, divide by the same exponent. Don't get too fancy and try and do everything in one step for a lot of these things. Take just 5 extra seconds and write this out and get it right. X. And last but not least, you need that plus a constant. And that constant gives you the most general antiderivative that you can get. Because when you differentiate a constant, no matter what it is, you get 0. So this is going to disappear if we took and checked it by differentiation. I should have ln of something there. It would be ln of x. The last thing to do is to clean this up. Dividing by 1/2 is the same thing as multiplying by 2. So overall, we'll end up with 2 ln of x plus 2 times the square root of x plus c. Okay, as we move into some more here, let me remind you, or maybe inform you, that there's a nice connection between derivatives and integrals. So for instance, I know that the derivative of sine of x is what? Derivative of sine of x is, help me fill in the blank.
Cosine x.
Cosine x, excellent. But here's the thing, when you apply the integral and the derivative are opposite operations. So if I were to apply the integral to both sides of this, then on the left-hand side, this stuff cancels itself out. The integral of a derivative of the sine. So I end up with the sine of x plus a constant is the integral of the cosine of x. There's this nice relationship that if you differentiate one way, you can find the integral the other way. And that's true for all of our derivative rules. So I tried to find one, and I think I was somewhat successful, except it keeps on wanting my email address. Sorry, not giving it to you. But you can Google a nice list of derivatives, and every rule for differentiation also turns out to be a rule for integration. So for instance, right here, the derivative of tangent of x is a secant of x. So you can integrate both sides and get the integral of secant squared is the tangent. So all these rules we have for differentiation become rules for integration. And that's a nice little relationship here. So in fact, let's keep an eye on 2 of these down here. right here. Secant, derivative of the secant of u is secant of u tangent of u. And derivative of tangent of u is secant squared. And I didn't do a good job of cutting this out. But we'll come back and take a look at things here. I want to integrate secant of t, 3 secant of t plus 7 tangent of t. All right, so that's what we'll work on next. Let me copy that down. I'm going to copy it down with x's as opposed to t's, because t's look too much like pluses sometimes, and I get frustrated with that. So I'll write it as secant of x times 3 secant of x plus 7 tangent of x. That'll all be dx. So if you look at exactly what I wrote, let's try and focus that a little bit better. That's better. Now, in order to find an antiderivative, I have to do a little bit of work with this. So what I'll do first is I'll distribute the secant and get 3 secant squared of x plus 7 secant of x tangent of x. And that's still all dx. If it helps us, we can split this up even further. We can use the so-called linearity properties of the integral. That's going to be 3 secant squared of x dx plus, I'll factor out the constant. You can't factor out an x, but you can factor out constants. 7 times secant of x tangent of x, and again, dx. dx is our differential. All right, so I've cleaned this up as much as I can, and now I got to look critically at this function and this one and ask myself, well, what do I differentiate that gives me secant squared? Whose derivative gives me secant squared?
Tangent.
Tangent. Excellent. So it'd be tangent of x plus, I need something that when I differentiate it, I get secant of x times tangent of x.
Secant.
Secant of x. And last but not least, I'll put in a constant, because when I differentiate a constant, I get 0. This gives me the most general antiderivative that I can get. So there's my answer right there. It's just a matter of finding a couple antiderivatives. All right. Comments on that one? Let's do some more here. A little bit ago, we did this one. We did integral of 2 times 1 over x dx. You can factor out the 2, 1 over x dx. Give you 2 times ln of x. And of course, when you're finding antiderivative like this for an indefinite integral, you get a c, a constant. We're going to build on this a little bit to construct a houseboat. So it's going to be kind of this general form. So I'll call this example F. And I'm going to integrate 1 over cabin d cabin. So kind of like up here, this and this matched. And when I integrate 1 over cabin d cabin, kind of like what I got here, I get the ln of cabin. But let's not forget our constant of integration. So that's our houseboat. Well, how is that our houseboat? Well, we've got a log cabin plus the c. Yay, we built a houseboat. All right. Don't forget to tip your servers. I'll be here all week. All right. Just having a little fun there. No chuckles, no groans, nothing? Ouch, tough crowd.
I like it. It was a good joke.
All right, thank you. Appreciate it. Let's go back to some actual problems. Let's see. So moving down a step, evaluate the integral from 0 to pi over 4 of 3 plus 7 cosine squared of theta over cosine squared of theta d theta. 0 to pi over 4. And I'm just copying this down for myself. So as it stands, this is not something that personally I know the antiderivative of. I have no idea. But we can whip this into shape into something for which we can find an antiderivative. So let's see how you do that. The first thing that I would do is rewrite that as 3 over cosine squared of theta plus 7 cosine squared of theta over cosine squared of theta, all that d theta. And I do like to see that differential term there. It does help out and make a difference. Can I rewrite this integrand a different way now? Let's start out with the easy part. How does this simplify?
You cancel the cos squared theta under the 7.
Awesome. Thank you, Chloe. So I get a plus 7 here. How about this? 3 over cosine squared. Is there another way I can rewrite that? And the answer is yes. Does anyone know another name for 1 over cosine of theta? Think back to your trig. 1 over cosine of theta is the same thing as
Secant.
secant of theta. So this is really 3 times secant squared.
Can we do like
I didn't quite catch all that, Sandy. What was that?
1 minus sine squared?
You could do that in the denominator, but it's not going to get you anywhere that's going to help you out,
Okay.
because you wouldn't be able to find an antiderivative for 1 minus sine squared. But you're right, you know, the Pythagorean theorem does feel suggestive here. But the nice thing about secant squared is that I know something that I can differentiate to get secant squared. What do I find the derivative of to get secant squared? We just did this one. What do you differentiate to get a secant squared? Tangent. So it's going to be 3 times the tangent of theta. And I need an antiderivative here now, because I got a plus 7. When I find the antiderivative, what's it going to be? Plus what? Somebody I haven't heard from today. Take your chance. What do I differentiate with respect to theta to get 7? Or what's the antiderivative of that?
7 theta.
7 theta. Awesome. Now, if you're tempted to put a plus c, you can, but you don't need one. Let's see that. Plus c. That's going to be between 0 and pi over 4, right? You get rid of the integral symbol because you found the antiderivative. Now it's just a matter of evaluating the function at these points. And typically you don't put the plus c. Let's see if you can't figure out why as I do this problem. So we'll start out by evaluating it first at the numerator. That is pi over 4, or the upper limit. So it's going to be 3 tangent of pi over 4 plus 7 times pi over 4 plus c minus all of that at 0. 3 times tangent of 0 plus 7 times 0 plus c. This part simplifies a little bit. So remember the tangent at a pi over 4 angle or 45 degrees.
Is it 1?
It is indeed 1. And that's going to be 0 plus 0 plus c. Three plus 7 pi over 4. Can anyone tell me why, in general, when you're doing a definite integral, that is one that has the limits, why don't we need to bother with that c there?
It'll cancel out.
Yeah, it's going to cancel out. Whatever it is here, I'll get it here and here, and you're subtracting. Those are going to exactly cancel. So you can put it in, but it's going to eventually come out. So most people don't bother to put it in the first place, myself included. Now, this is something, again, that you can check on your graphing calculator or something like that. But what your graphing calculator is not going to give you is the nice exact form of this. They'll give you a number which is the decimal equivalent of this to a point, but they can't tell you that, oh, that's really 7 pi over 4 plus 3. So nothing wrong with checking yourself on that. This would actually be kind of a little pain to put into your calculator. I don't know. I don't think it recognizes cosine squared like that. So what you're going to have to do is put it in as cosine, let's say you use an x, cosine squared like that. That'll recognize. If you did cosine x squared, that's something different. So kind of a pain there to check it, but you can. Any thoughts on that one? All right. This one's kind of a good one. I like it because it reminds you of the nature of what the integrand is giving you. So let me just paste it over here. So it says W prime of t is the rate of growth of a child in pounds per year. What does the integral from 8 to 6 of W prime of t dt represent? Well, when you're integrating something, you're finding an area between a curve and the x-axis. So in this case, you've got a curve that represents how a person's weight is changing throughout the year, or at any particular time. Now, if you look at that area, how the rate is changing as a function of time, so 6 to 8, but imagine that a healthy kid should have, a pretty good weight gain, maybe lost a little bit of weight during summer sports or something like that, A to B. With this area, assuming that this is your weight change, this total area is going to be the total amount of weight that you gained in this time interval. And in our case, it's 6 to 8. So it's how much weight did the person put on between ages 6 and 8. So we look back at this. The change in the child's weight in pounds between the ages of 6 and 8. I guess I said weight gain. I'm assuming that the child would be gaining weight. I hope they would, between 6 and 8. So another place that you'll see rate of change as part of problem is with acceleration functions, acceleration, position function, etc. So let me remind you a little bit about our notation for some of these things. We'll go back and revisit them. So S of t is your position function. V of t is the velocity function. Now, your velocity is how you change position. So V of t is going to be what compared to S of t? The way you change your position is your velocity. So the rate of change of that is measured by the derivative. So S prime of t gives me V of t. And the last one that we're going to deal with is A of t. You remember what A of t is?
I said acceleration.
It's your acceleration function. Excellent. Now, if I know what V of t is, how would I calculate A of t?
Take the derivative of v of t.
Excellent. So A of t equals V prime of t, or it equals S double prime of t. Either way, it's the second derivative of the position function or the first derivative of the velocity function. Okay. So with that quick reminder, let's look back at the problem. Give you a couple more seconds to copy this down if you're copying that. So we got an acceleration function, A of t equals t plus 4, and V of 0 equals 6. 0 less than or equal to t less than or equal to 10. This is find the velocity at time t. All right. Well, they give us a little information here. And that information is that the velocity at time 0 is 6. So what does that tell us? Well, in order to get the velocity function, I've got to take the antiderivative of V of t, or excuse me, of A of t. So in other words, if I integrate A of t dt, that gives me the velocity function plus a constant. So let's find the antiderivative of A of t. T plus 4 dt. That's going to be t squared over 2 plus 4t plus a constant. That's my velocity function. But I want to know the velocity at time 0. So, let's see. Velocity at time 0, in fact, they tell us velocity at time 0 is 6. So V of 0 equals 6. That's also going to equal 0 squared plus 4 times 0 plus c. So in other words, that's 0 and that's 0. I end up with 6 for c. I can put that in for my function now. That's going to become v of t equals t squared over 2 plus 4t plus 6. Nice. So there's your velocity function. Are you okay with that calculation?
Yeah.
All right. Now there's one last part to this, and that is to find out how far you traveled during the time interval 0 to 10. So let's take a look back. It says find the total distance, find the distance traveled during the given time interval. Well, the distance traveled is going to be an accumulation of your velocity. So it's going to be the area underneath the curve of your velocity function in the interval 0 to 10. And that area is simply going to be the integral from 0 to 10 of your velocity function, t squared over 2 plus 4t plus 6 dt. Let's see if we can't find an antiderivative here. What you might want to do, especially with that first one, is kind of split that up a little bit. Might want to write that as integral from 0 to 10 of 1/2 t squared plus 4t plus 6. But writing it as a fraction and pulling that fraction out in front is not a bad idea, because then you can just concentrate on integrating that. That's going to be a function evaluated at 0 to 10 of 1/2. And then what? What happens when I try and find the antiderivative of t squared? What will I get?
T cubed over 3.
Awesome. T cubed over 3 plus 4t squared over 2 plus 6t. Now, this can be simplified as, say, 1/6 t cubed. That can be simplified as 2t squared. But those are things that it's not a bad idea to do them after you found the antiderivative. Because what I see is a lot of times people trying to get this perfect right away. And it's hard. It's hard to get this perfect right away unless you're breaking it up into little steps. So that's what we'll do, break it up into little steps. So cleaning that up, 0 to 10 of 1/6 t cubed plus 2t squared plus 6t, 1/6 times 10 cubed plus 2 times 10 squared plus 6 times 10. Minus what happens at 0. But if I put in 0 into this function, what am I going to get?
0.
0. So I just typically put like minus 0. Just to maybe remind myself that there was a 0 there, but that's it. I don't generally put anything really big there. So if I clean this up a little bit, let's see what we're going to get. 1,000 over 6 plus 200 plus 60. So 260 plus whatever. Plus, yeah, I should know that. What's 660? 6? 1,000 divided by 6. Yeah, 166 plus 260. Okay. Let's pause here. Comments or thoughts? Okay. So for a second, I was getting a little nervous because I remembered seeing the answer had a 1280 in it, but I didn't notice it was divided by 3. So it does work out to be our answer. I should probably be conscientious enough to include the units. They're included for you in WebAssign, but let me include them here. Units would be meters. So let's continue with a few more here. And what I want to work on next is this one. The integral from 1 to 4 of 1 over x squared minus 8 over x cubed dx. Now, sometimes it's not a bad idea to look at these things. So let's take a quick look at this with Desmos. And I'm just going to open up a new page here and graph it. Because the areas involved can tell you whether or not you expect a positive or negative answer. It can help you double check your work. If you expect something positive and get something negative, then there's a problem. So my function was 1 over x squared minus 8 over x cubed, and I want that in the interval 1 to 4. Oops. Not there, over here, here we go. So there you go. So this is the interval that we're working with, and that's the function that we've got. Do you expect a positive or negative answer here? What would you suggest? What would you think?
Negative.
Yeah, I'd say negative. All right, so let me see if I can't shade this. There you go. So there's the area that you're dealing with, and this area lies below the x-axis, so you would expect a negative answer. Now, if you have that in mind, then you're not going to be surprised. To get going on this, I'd rewrite this as x to the negative second minus 8x to the negative third. It's still in the interval 1 to 4. Then you need some antiderivatives. Now, as always, add 1 to the exponent and divide by that same exponent. If I add 1 to this exponent, what would I get?
Negative 1.
Negative 1 divided by negative 1. Okay. Minus 8 x to what power?
Negative 2.
Negative second.
Negative second divided by negative 2. Thank you, one and all. Between 1 and 4. Now, before you start evaluating these things, let's clean this up a little bit. For instance, I've got x to the negative first. That negative can come down to the denominator. And I'll write the negative out in front. So negative 1 over x. A negative cancel each other out. Plus 2 and 8, that cancels. It gives me a 4 over x squared. So that's looking a little bit better. Let's plug in our limits. Plug them in at 4 and again at 1. And I'll get negative 1/4 plus 4 over 4 squared minus negative 1 over 1 plus 4 So let's see. Oh, those will cancel out. That's just going to give me 0, right? Because it's going to be negative 1/4 plus 1/4, so that's going to be 0. 0 minus 3. So negative 3. Yay. Let's just double check ourselves. And I'm not sure why my graphing calculator software isn't working for me today, but we can check it this way. Math 9, integral from 1 to 4 of, I'll just write it as x raised to the negative second minus 8x raised to the negative third. And you got to tell your calculator what you're integrating with respect to, so that would be x. Negative 3. Perfect. Nailed it. Now, it's nice to see that there. With our next one, I'm thinking we might get a decimal answer that we could check, but we're not going to get an exact answer out of our calculator for the next one like we did the last one. Before I move on to our next example, are we okay with things here? Notice that I rewrote this so that I could use what we know about integrating things with exponents. You add 1 to this and then divide by that same exponent. So when I added 1, I got negative 1. Divide by negative 1. Add 1 here, gives me negative 2. Divide by negative 2. These match. And it's only after I've written this do I try and simplify. But make sure that when you're doing this, at least initially, you'll see that these match. And these match. Take your time in simplifying this. I see a lot of mistakes in people doing that. Turning our attention over here, I'd probably rewrite this as 3 times integral from 0 to pi of e to the x dx plus something. What else could I write here? What else do I need to write here in order for it to be equivalent to what we had up here? Notice, for instance, I factored out the 3 because 3 is a constant. What would I write here?
Factor out the 8.
Yeah, factor out the 8. 0 to pi, sine of x dx. Okay. I need somebody to think long and hard and come up with the antiderivative of e to the x. What do you differentiate to get e to the x? Kind of a trick question. Derivative of e to the
E
x
to the
is
x.
e to the x between 0 and pi plus 8. And sine's always a little bit of a pain. It's all right, we can figure it out. What do you differentiate to get sine? And the answer is not cosine. Because what's the derivative of cosine? Derivative of cosine is
Negative sign.
Negative sign.
negative sine. So if I find the antiderivative of this, I'm going to get negative
Negative cosine.
cosine of x. All right, so over here, I'll get 3e to the pi minus 3e to the 0. That's coming from that term right there. Basically 3e to the pi minus 3 times or plus this right here. So if I plug in pi, I get negative cosine of pi. What's the cosine of pi? Cosine of pi is going to be Yeah,
Negative
so
one.
negative 1. Negative 1 times negative 1 gives me positive 1. So 8 times positive 1 minus 8 times negative 1, because cosine of 0 is going to be 1, but I've got negative there. So negative, I think it's going to end up being a plus, like that. 8 times 1, 8 times 1. So let's take a look at what we're left with overall. That's going to be 3e to the pi minus 3 plus 16 equals 3e to the pi plus 13. And you can check that on your graphing calculator, but all you're going to get is a decimal value of this. And then what you might want to do is compare that to the decimal value of 3 to the pi plus 13. See that they're the same. All right. You want some more detail here? I was a little bit sketchy on that part. Or here, and just combine like terms. Just hope we're good on that last step. But is there anything about this one that still left you scratching your head a little bit? Not sure what I did. In stuff like this, it might not be a bad idea to clean this up a little bit, maybe factor out the negative. So you get negative 8 times cosine of x between 0 and pi, and just leave the negative 8 out front. Negative 8 times cosine of pi would be negative 1 minus cosine of 0. So minus cosine of 0 is really minus 1 again. Negative 8 times negative 2 gives you the positive 16 that I got up here. So hopefully you feel a little bit more comfortable with that. And like I said, it's not a bad idea to factor out the 8 and just distribute it in at the end. Now, back at the start of this, one of the things we looked at was antiderivatives, just in a general sense, finding the indefinite integral. And what that leads to is a constant. So let's take a look at the effect of that constant. So this, for instance, is the antiderivative of negative sine of x plus x over 9. All right, so if I integrated integral of x over 9 minus sine of x dx, what we'll end up with is x squared over 18 plus cosine of x plus a constant. Now that constant is there because when you differentiate something, the derivative of a constant goes to 0. So both of these work out pretty good, and the derivative of constant goes to 0. So we're okay there. But this gives you an entire family of possible solutions. Any value of c here is going to work. You put in any value of c and you differentiate it, you're going to get this. Now, a lot of times you'll specify something about your function so that you can actually determine the value of c. But sometimes they're going to want you to write just general functions. So in this particular case, I've drawn two different curves here with different values of c. I let c equal 1, c equal 1, c equal 3. What other values of c can we put in would be of interest? You put them in with a comma. So comma, say 5. There's another one. Maybe you want to see what happens when c is 0, comma 0. So let's see, comma 0. There you go. There's c equals 0. You can put in c equals pi. Whatever values you want. Now c equals pi is pretty close to this one, so let me just delete that one. But you get this family of curves. Now notice what's consistent about these is their shape. The derivative at any point for this curve here, this top one, is going to be the same as the derivative down below. The only difference is that you've shifted it up by that constant, but it doesn't affect the shape of the function. So that's one way you can do multiple graphs, because there is a problem in your homework that requires you to look at multiple graphs. And alternately, you can do that kind of thing, not quite as elegantly, but you can do it on your graphing calculator. You can do, for instance, x squared divided by 18 plus cosine of x plus 1. And then type in that same function again, except plus 3. So, or make it 2 bigger. So x squared squared plus cosine of x. Oh, this should be x squared over 18, my bad. Divided by 18. There we go. Plus 3. And so what should happen is that these functions should be just shifted from each other, like the ones we were seeing on Desmos. But that's kind of a brute force approach way of doing this on your graphing calculator. And then you set up your window correspondingly. -6 to and -6 to 6. Something like that. 0. There. So those are different values, same family of functions. So we'll add in one last graphing calculator trick. And the trick is to be able to graph multiple levels of this without quite as much of a brute force approach. So once you get the first function in, let me clear this second one out. So I'll clear that one out. If all I want to do is take that and maybe add 2 to get to the next one, easier than typing that in, you could hit vars and then go to the right one and hit y vars, press enter and select, oh, I want function 1, except I want to add 2 to it. And you get the same thing. You're just going to get a level curve that's a little higher, 2 higher. I can do that and add 4 if I wanted to. And to remind you, there's a different way that you can get to the y1s, y2s, etc. And a faster way to do that is to hit the alpha key, then the trace key. There's your y1. So I'll just press enter. And this time I'll add 4. And now I'll get this curve, except shifted up by 4. I've already got my window set up, so let's hit the graph key, 1, 2, and 3. Beautiful, just like that. So once you get that first function in, maybe that's a little easier to do it this way. All right, so I think that'll do it for section 5.4. The homework should be available, so good luck on that.